This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right. So in the last lecture, we discussed a different type of conduction heat transfer, which is utilize the extended surface, and in particularly the subject we discussed is using a fin-like structure, and we conduct the analysis to the fin and derive the equation so that we can understand how the heat transfer going through a fin. So the extended surface heat transfer, the purpose of it, we want to be clear, that's to enhance the heat transfer. So you give it a more surface area, so heat transfer can happen both through the conduction and convection mode. Right, so let's quickly review what we analyzed so that we have a clear understanding of what we analyzed, not just in terms of the equation we derived, but also physical understanding of the process. All right. So we want to determine how much heat can be dissipated through a fin, and that heat is coming from the base. Right, the fin is usually is additional structure we add onto it, so that to help us. But what you really want to quantify or want to know that whether the fin is working or not is how much heat it can dissipate, which is through the fin base. So that's Q0, or sometimes called QF, right? So that's coming from the fin, and this one has certain geometry. So the thickness, length, and width, right? And then we have the convection, which is happening, which is on the fin surface. So it's important to notice, although we often only draw this on top of the fin, it happens on all the exposed surface, on the top, bottom, and the sides. All right. And then what we did actually, we want to find out the temperature distribution as a function of x. So if that's x direction, we want to know how the temperature distributed along the fin, which is this means it's a local property, and so this Tx, the Tx and the Q0 both are our targets, right? So we can get the Q0 after we know the Tx. So this is a local property. To find out the local property, which means we need to start with a local volume. A local volume means a infinitely or a finite control volume, essentially. And what we did is we just choose a slice of the thing along the thin length. So it's not being done without a reason, because we want to know the local temperature. So which means we need to starting with an analysis or analyze the local volume there. So based on that, that's the first control body we choose. So that's a very important first step. Then we apply the energy balance there, right? Energy balance is in plus gen equals to out plus change. So we're dealing with a steady problem, and we're dealing with a case without heat generation. So basically, on this control volume, what we applied is Q conduct in equals to Q conduct out plus convection. Right? So the energy balance we applied on this differential control volume is the heat is coming in as a conduction and leaving the same surface area as a conduction, but at the same time it got lost through the surface of the control volume and as a convection. All right, so that's the things we want to be clear with, and you want to understand the purpose of the thing. Essentially, is to utilize convection to dump the heat. The convection basically, the conduction basically is a means to allow the heat to transfer a certain direction, but all the heat actually got lost is due to the convection. Because that's the heat, the conduction or the heat leaving the control volume is not got lost, right? It's a heat that is convected from the surface area that actually got lost. All right. Certainly, at the end, we need to dealing with the specific condition at the tip. But other than that, it's basically all the heat is lost through convection. Then what we did basically is following the procedure we described before. We bring in the rate equation for conduction and convection, and then do the integration, right? And with the integration, we'll find it's a second order differential equation, and then we need to bring in two boundary conditions. One is x equals to 0, and one is x equals to L. Right? X equals to 0, basically, you can consider it's a given, and where temperature equals to the base temperature, and x equals to, as a tip, we have 4 conditions. We discuss them in different ways. So there is a few which is more theoretical, like the infinity long or the adiabatic, and some others which is more practical, which you can consider is a convective tip, which means the conduction heat loss equals to convection at the fin tip, or you have a prescribed temperature at the fin tip. Right? So you just choose one out of the 4 boundary conditions as a tip to solve the problem. And the solution already being given as you don't need to derive them, and you don't really need to remember them. So that's the things we studied from the last time. And once you solve the temperature, and you want to find the Q0, right? The Q0 is something we know if we know the temperature, which means it's using, if we know the temperature distribution and we find out the heat transfer at the base. What do we do? So at the base, which means you have only conduction coming from the base there, right? The base has no exposed surface area if you have a fin. So in that case, you just apply the Fourier's law. So you have the Q0, which equals to minus K A cross-section area, and then you have the dt dx and x equals to 0. So basically, you know the temperature distribution, and the Fourier's law tells you how to connect the temperature gradient with the heat transfer rate, and you set it at the condition that you want to know. All right. So that's how we derive it. As we said, this is you can consider it's a standard process we are doing here. And pick the control volume and apply energy balance, apply the rate equation, integrate, choose the right boundary conditions, then get the equation. And then if the problem asking you solve any numbers, you just check in the numbers that are given in the problem. Right? And if we understand the process more physically, if I say what's the temperature, how the temperature going to vary along the x. So if x going up, the Tx would goes down, goes up, or no change. So along the x direction, along the fin length, how the temperature will be varying? So by intuition, that should decrease, right? No way it will increase because there is no way, there is no heat being keep added along the length. So all the heat is added from the base, and then you have the heat loss along the way. So the Tx, you may not know how the exact function of the Tx, but the Tx must be going down. That's something you definitely want to know. And how about the Qx? So the heat transfer along the x. So the heat, again, if you consider the all the heat is coming from the base, right? All the heat that is coming from the base, and along the way you have the surface which got exposed to the ambient convection. So the heat must got lost by convection along the way, right? And when it's got lost, what happens to what is only the remaining heat which is being conducted along the way, right? So Qx must also going down. So I'm talking about the local value. The total is always, or the integrate heat loss must equal to the Q0, but along the x, locally the Qx must also going down. All right. So that's the physical understanding that we want to have, and so the other things, the important thing that we want to discuss next is called the fin performance. So as I said, the fin almost always is additional structure or is artificial structure you added in order to enhance heat transfer. So whether it's necessary or whether it's worthwhile to have that structure or you spend your effort to spend the money to add a structure to it, that needs to be known, right? If it's you find out it's with the thing, the heat transfer is not being changed very much or not being enhanced very much, then you want to think of some other ways to enhance the heat transfer. All right, so that's related to one property called the fin effectiveness. So the fin effectiveness is defined by epsilon, and it's a ratio of two heat transfer rate. So one is the heat transfer without fin. So the numerator is a heat transfer with fin. So we want to compare the two cases. So in one case, it's just a bare surface, which means you only have the base here. There are no fin being added, and the other one with the fin added. Let's see whether the fin is going to help us or not. Right? So that can be expressed in the equation. So the heat transfer without fin, which means we only have the base surface, and the convection still happens. No fin to conduct anything, but the convection still happens on that base surface, right? Without fin. So which means if we write the heat transfer for this case, there will be H area, and this area would be the base area for our topic here, which is the fin has the constant cross-section area. You can just using the HAC to stand for that, and then the convection happens there. So the T0 minus T infinity. So that's the case. You have a bare surface without add anything. The other one is the with fin. So let's say this is a Q fin case or Q0, and we know there is a 4 conditions, right? So we will use a special case, which is an infinite fin as an example. Although infinite fin is not really practical or it's not real, but by bringing in its heat transfer rate here, and we can have a pretty good understanding in terms of what are the parameters that are affecting the fin performance, particularly the fin effectiveness. All right. So the QF, if you remember the equation or the table that I showed last time, so this one is basically can be written as I didn't bring that table here, but it can be written as HPKAC T0 minus T infinity, then HAC T0 minus T infinity. All right, so this one, if you're looking at the table, this one is the capital M there in that table. And again, this one is for the infinite fin, which we used as an example here, just to show different parameters affecting the fin performance. All right, so these two got cancelled, so that's no problem. And then we end up with that's P, K, and HAC. So that's the 4 parameters which directly related, some related to the material of the fin, some related to the geometry of the fin, and some related to the ambient convection coefficient. right? So let's look at what different impact can have here. So this one saying that when K increase, K is the thermal conductivity of the thin material, the thin effectiveness must goes up. Right, so this is straightforward to understand. So if you using aluminum or using copper, you will have the heat will be dissipated more through the thing. So that's straightforward. You don't want to using some insulator to build the thing. So the this one is high K material. For example, aluminum to build thing. I should say use high K material to build the thing. All right. So that's often the case, and for a car radiator, so you see there is a lot of small things there, and they are typically made of aluminum, which is cheap and light in weight. So that's straightforward. And the other one is we have two parameters related to the fin geometry. So one is P. P is the parameter here. So which means the P is a parameter of the fin, and the AC is a cross-section area of the fin, right? So if we write as P over AC from the equation we derived, so if this ratio goes up, so that's coming from here, if this ratio goes up, the fin effectiveness will also goes up. So how do we understand this? So if we can express P's parameter can be written as 2 times width time plus T. So that's the parameter, and then twice, right? Divided by the cross-section area of the fin, which is WT. Right? So we know that the W is generally much larger than the T. So the width is often much larger than the thickness. So we can write, because the W is much larger than the thickness, then we can remove the, we can get rid of the T in the numerator. So basically 2 times the width over WT. And then the W got cancelled is 2 over T. Right? So this one is saying that when T goes down, the effectiveness will goes up. So this one saying that when you adding a thing in order to enhance the heat transfer, you want to using a thin fin, right? The fin needs to be as thick or as you can afford. So use thin fin. Thicker structure wouldn't help in this case. You want to use the a material with higher K, but with a small thickness, right? So that's that, and the other one is the H. So if we're looking at the equation we derived here, H saying that if you have a smaller H, then the fin effectiveness will goes up. Right, so this one saying that if the heat transfer coefficient of your ambient fluid is smaller, then the fin will be more effective. Right, this is sounds a little bit strange. Is it? Because we know the H is a convection heat transfer. If we have a larger H, we have a higher heat transfer rate, right? But this one saying that if you have a smaller heat transfer rate, the thing will be more effective, right? So this is related to any idea in terms of how to understand this impact. So that's related to how do we define the thing effectiveness. This one is defined based on a case with thing and without thing. This definition is not necessarily related to the absolute heat transfer rate. Right? This one just saying that if you have a case that you want to install thing or you do not want to install thing, then for the case that the ambient heat transfer coefficient is smaller, then you will have the thing will work more effectively. Not necessarily saying you will have a larger heat transfer process, but the thing, the action of add a thing to the bare surface will be more effective. All right, so that's you want to understand, which is saying that if you have a choice, for example, you have a choice that you can put the thing on either towards air or towards the water. For example, you have the water flowing in a tube or like a coolant or hot water that you want to cool. And then you have the air, which is flowing outside, right? And we haven't discussed that, but for liquid, the heat transfer coefficient H is much larger, order of magnitude larger than the air. So the H there is much larger than H of air, right? This one saying that in this case, if you want to put the thing to enhance the heat transfer, do not put the thing inside. You want to put the thing on the side, which has a smaller H. So this one is a but. So you want to put the thing on the air side instead of inside. Even though inside the H is larger, but it doesn't help in terms of giving a more effective thing. Right? This is a little bit counterintuitive, but if you understand how this effectiveness is defined, then that's okay. And if you combine with this practical example, for example, for all the radiator or the evaporator we saw in the refrigeration lab, those things all on the air side, right? The coolant or the refrigerant is flowing in the tube. And outside the tube, you have those thin structure which is exposed to air. We don't put those thin structure inside the tube for the to facing the fluid, to facing the liquid, I should say. All right, so install the thing on air side for higher effectiveness. So that's related to how this effectiveness is defined. All right, so that's the basically the three parameters that we discussed. If we consider is an infinite thing, but often the length of the thing is something we also want to know. But for infinite long thing, we don't have those parameters in the heat transfer rate, right? So in order to know the length, so let's say, what about impact of length? So in this case, let's use another case or another tip condition as an example. So let's use the adiabatic tip as an example. Because with adiabatic tip, we have a length or air term in the heat transfer equation, or heat transfer equation, solution. All right, so in that case, we have the effectiveness. Again, it's defined as the HAC, the heat transfer rate without anything. And if you're looking at the solution we had the last time, this one can be written as HP KAC and hyperbolic tangential ML and times T0 minus T infinity. So in this case, again, this got cancelled, and we end up with something like PKHAC tangential hyperbolic ML. So for a given structure, these are the parameters we already discussed, and they are also fixed. And the variable here is air. So when air increases, this hyperbolic tangential will goes up, so the fin will be more effective. So that's understandable, which means, again, if you consider how this effectiveness defined is with fin versus without fin, right? If you have a longer fin, you always got more heat being lost through the fin surface. So which means it will always be more effective. All right, but should we if we want to get a higher effectiveness, should we using a fin as long as possible? So that's related to another parameter that we use to evaluate the fin performance. That's called fin efficiency. All right, the fin efficiency is defined in a similar way as the effectiveness, but certainly they are different. So this one is saying that, again, it's a heat transfer with fin. It's normalized by another heat transfer term. So in this case, it considers that all the fin, consider an ideal situation, okay? Consider that all the exposed fin surface is at the temperature of the fin base. So basically consider all the exposed fin surface area at the same temperature as the fin base. We already said that along the length, the temperature is actually dropping, right? You wouldn't have the same surface temperature as a base. So, but this one is considered ideal situation. So the heat transfer with all the fin surface at T0, which is a base temperature. All right, so we can write the equation for this case. So if we consider the heat transfer for all the fin surface area, so we have H area of the fin, right? And then the temperature difference is a constant, T0 minus T infinity. And on the numerator, we choose the case of the adiabatic fin, just for the discussion purpose. So that one is equals to HP, KAC, hyperbolic tangential ML, and T0 minus T infinity. Again, that's the adiabatic tip as an example. All right. So the fin surface area we can express a little bit further. So if we consider the fin surface area here, we can use the parameter, which is the P, the parameter times the length. That will give us the fin surface area, right? So this one can be written as P times L. And then we can further just simplify. We would have the KAC over HP and times L and the tangential hyperbolic ML. All right. And then if you looking at the notes we had last time when we solving that second order differential equation, we defined a parameter called m0, or not m square, lowercase m square. And then there you can find this term actually is equals to 1 over m. So this term is equals to 1 over m based on the definition we had there. And then we have the ML times the hyperbolic tangential of ML. Right? So then we notice that how the fin efficiency is going to vary with respect to length. So we know that when length increase, the m for the problem is a fixed value, right? For a given geometry except the length, and for a given material and given the ambient fluid, then the m is a fixed value. So when you have length increase, the ML will definitely, 1 ML will definitely decrease, and the tangential, hyperbolic tangential ML will definitely increase, right? So there's two competing factors. But if you plot it, you can find that this term decreasing much faster compared to the increase of this term. So this one drops much faster. I should say faster than the increase of the other term. So overall, you would have if the length increase, then the efficiency will drops. Sorry, I should say the fin rather than the thermal efficiency. It should be the eta fin, okay? So which means the longer fin actually will drop the efficiency based on the definition here. So that's saying that even though the longer fin will make the heat transfer process more effective, which means the epsilon will increase, but the efficiency will decrease. So if I can draw this, so these two will vary in opposite way in terms of length. So if this is a 1, it drops like this. So that's the efficiency, and the effectiveness is going up. Like this. And typically I should say the effectiveness needs to be, this value needs to be greater than 2 in order to justify that you put on a fin, right? I should say that the should be greater than 2 in order to justify the fin installation. But the point here mainly is about these two will vary in the opposite way. a longer fin will be a less efficient fin, although a longer fin will be more effective. Effective, which means absolute amount of heat, it will dissipate, we are going up. But for the area length that you add, it will be less effective. So you can understand this as a diminishing return. At the start, or I should ask, what's the case for the most effective, most efficient case? What is the most efficient case? Yes. No fin? Yes. So when you have a bare surface, that's the most efficient, based on the definition here. That's the most efficient case. Because as soon as you start to add a fin, the surface temperature will drop, right? So if I can draw so if this your ambient temperature, which is remain constant, and you have the base temperature, so as at the zero length, you have the largest temperature gradient, temperature difference to drive the heat transfer by convection. The Q is the highest in that case. As soon as you start to add certain lengths, if L1, then the temperature will drop at that point. The more you add L2, L3, the more you add, the temperature will drop more. And basically you have a curve like this. So the smaller temperature, which means the heat transfer rate, Q, by convection will be smaller, because the H and the area are essentially the same. The only parameter determining the convection heat transfer is due to the temperature difference. You have a small temperature difference between the fin surface temperature and the ambient, which means less amount of heat you can lose per unit length or per unit area. So the fin will become more and more inefficient as the length goes on, even though the absolute heat that dumped through the fin will be higher. All right, so that's some physical understanding that you want to have. All right. That's the one for the discussion we having here, and you can have the what we discussed here is a simplest case, which you have a single fin, which is have a uniform cross-section area. In reality, or in practice, often that's not that simple, and often you are dealing, you barely using a single fin case. One thing probably I shouldn't forget here is because the fin efficiency will decreasing along the length, so you do not want to using a single fin, but rather you want to using a multiple short fins. Right? That's actually the case that you see in reality. So I should say the air increase, efficiency decrease. So which means for the guidance of practice, use short multiple short fins instead of a single long fin. All right, so that's related to in practice. We do not, in terms of calculation, we do not dealing with a single fin. We're dealing with multiple fins. For example, even we still stay with this rectangular fin. It often there's many of them being put together. Right? So assume all of them are the same. So in this case, how do we determine the heat transfer in this case? So you have the Q fin still coming into each fin. And at the same time, for the surface without the fin, it still got a certain surface area, and the convections can still happen on those unfinned surface, right? So you have the, let's say you have the T infinity and H as ambient. So in this case, basically the total heat transfer is a pretty straightforward. Essentially, the total heat transfer equals to the single fin times the number of fins there. And then you consider the heat transfer on those base or bare surface, so the Q of the base. So this one you can using the equation we derived last time, and then times the number of things, and this one basically is H times A base times T minus T infinity, T0 minus T infinity. So show that this is right, so that's pretty straightforward. But here it assumes that you have a uniform temperature at the fin base, regardless whether you have a fin there or without a fin there. So you have uniform temperature, T equals to T0. So that's assumption. And also you assume the heat transfer coefficient on those. You assume an averaged heat transfer coefficient for the entire area. Doesn't differentiate the local H, which can be different here, 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 or there. But you are just assume an averaged value. All right, and obviously the geometry of the thing doesn't have to be like this. Doesn't have to be a rectangular. You can have a triangle, or you can have a cone, or the circular. So those geometry we are not going to discuss here, but that's basically have been figured out and tabulated in the textbook. So if you has a need in the future to dealing with those structures, that's available in the textbook. Right, I think that's all for today. So tomorrow I will do a demonstration, and that's related to the second assignment. So make sure you'll be here. Yeah. So you send me email. Oh, yeah. Is that the short one?
Yeah, it's short term. I know the short term related to economics for my major in chemical engineering. I know don't have short term. That's I said some reasons. For the first one is I have a non-gradient class, so I need to select another elective subject to make up. That's what I want to do. I want to use this.
But is that program approved by the university?
I know, but I have checked for the installment for me. For the first step, I must get on it.
My job there is to basically you submit a subject, and I find it is equivalent to one subject in your degree, and then I prove it. So sometimes for the short-term exchange, you often need two subjects in order to have one subject credit back. And but that's even for that, not all the short-term are approved. So I proved one for Peking University once. I haven't approved any others in terms of short-term.
I know. But I know I missed the deadline of Peking University for the engineering. I know this program is related to the engineering, but I missed the deadline. I asked some coordinator of this project in South, and they told me I have to end Fudan University first, so they can't tell me to transfer it. And the Peking University also sent me the email, and they can help me to ask the minimum. Do you know whether I have opportunity to discuss this one?
This program needs to be. I mean, because I'm only looking after the mechanical engineering, so this approved it needs to be approved.
Just some submitted form.
No, if it's the program needs to be approved by the entire faculty.
Yeah.
So, which means not only mechanical engineering students can take it, like the infrastructure, electrical students, they can all taking the related subject. Yeah. So, it's about approval of the program. It's not about approval of the subject you are requesting. So that's. I mean, I said the only short term I proved so far is for the Peking University. I haven't got a request from the engineering faculty saying that we want to add Fudan short term exchange into our exchange program, so our student can go there and do short term exchange. So that's a different thing. Like the Nanyang Technology University in Singapore. They have a similar program, but they haven't. I haven't got any request in terms of our student can go there and do short-term exchange.
Oh yeah.
That's different. Short-term is quite different because we are not so sure about the quality or the times and hours that the students spend there to get enough credit.
Oh yeah. I know you mean. So I don't have any chance to do it for Fudan.
I mean, so far I haven't got any. Is this for the July?
June, July. Yeah.
Yeah. So, yeah, I haven't got anything from. I mean, I can ask our engineering exchange like coordinator in terms of whether we want to do this or not. But I haven't got any request in terms of proving subject in that program.
Yeah, it's okay. So, but this is deadline this weekend. So, would you mind to?
I can ask them if I can get the reply
Yeah.
soon. Then I can work on it. If they don't reply me, then I don't.
It's okay. It's okay. Thanks. Thank you very much.
Yeah, it's okay. Right.
This was on left the fourth one. The Apple AirPods.
Oh, okay. All right. Right.
$320.
Yeah, no, people will be upset about that.
All right. Thank you.
Just a couple of quick questions. When you're choosing effectiveness and efficiency, was there a specific reason for using infinite tips and adiabatic tips, or was it just to highlight properties?
Yeah. Theoretically, you can using any tip, but this basically is to illustrate the parameters affecting the film performance. Yeah. So those are the simplest one, which is easiest to demonstrate.
Are we going to be expected to remember these sort of things, or will they be provided?
I mean, the equation, no, but the factors. For example, if whether the thing should be thicker or thinner in order to be more effective, that's something you need to.
Yeah, that makes sense. And just a quick last one. In a situation like this, you'd have a bit of Q radiation going this way and this way and this way. Would that be negligible to the temperature here? So, okay, we can discount that.
Yeah. So depending on the temperature the radiation is happening.
Yeah.
So
high temperature would be.
Yeah. High temperature definitely would be more important, which is hard to ignore the radiation. But often, when we're talking about the convection, the H has a lot of uncertainty in terms of determine the exact value, and often that's coming from the correlation, empirical correlations. So that if the radiation is not significant, or you can lump all the uncertainty into the H.
Okay, yeah, I see. Just sort of combine it. Yeah.
Yeah.
All right, thank you.
Yeah.